Yes.
You just made it full
Yeah,
screen.
perfect.
All righty. Okay, if I get started?
Yes, please.
Okay, so hi everyone. I'm Vanessa Sockett. I am a principal computer scientist at Lawrence Livermore National Lab. I'm joined today by my colleague, Dan Milroy, and we're going to talk about hybrid quantum and classical workload management with graph-based scheduling. Because I can't see you, I will take questions at the end. So let's get started. Now, a lot of us as system software developers, we have this question, what might the future look like? And many of us may agree that the future is hybrid and autonomous. With the emphasis for the context of this meeting with hybrid, we are asking the question, how do I run classical and quantum workloads? But it's a little bit more than that. It's how do I co-schedule these workloads? Now, I want to argue to you that the kind of a good way to think about the designs for the scheduler are first to think about the designs for the actual applications that are using quantum. So let's take a look at some of these designs. This first design I'm calling a single evaluation. This is actually the unit that constitutes the other designs. And so this is what you'd imagine. You build a circuit, you have your circuit, you send it to a device with some number of shots for a task, you get back the result, you read it, signed, sealed, and delivered, you're done. Now, when we look at QAOA or BQE, we get what looks like a loop. And so for this design, you might start on your classical resources, you build your circuit, you send it off to the device, you get back a cost or energy, and then you send it back to the classical resources. And then you tweak your parameters and you keep going in a loop until you reach some kind of convergence or you minimize costs, for example. It's a cycle. The third is batch, the embarrassingly parallel case. You might have n independent circuits that each go to a device. Maybe they can arrive at the device at different times. You get different results, and if you need to process them at the end, you probably just need something like a barrier that will make sure that they all are arrived, they're all finished. And pattern 4 is the fan out. This is still having a circuit, sending it to a device, getting it to a result, and then sending it off to a bunch of post-process consumers. So this asks the question, how does application design influence scheduling? And this is exactly what we started to think about when we started to think about our scheduler Flux framework with respect to quantum. I'm going to give you a very simple answer for how I've been thinking about this. When my application expects a resource, it needs to be there. And so there's a couple of things that can happen when it's not there. So if you're using something like MPI, your entire job may just die and fail. If your application is resilient to that, it's probably going to sit around and wait. And so neither of those two things are ideal. So let's talk about some scheduling designs generally that might help with these application designs. Again, I like asking questions. I want to now ask, how does resource design, so the interfaces, for example, that I'm using to interact with quantum devices, how does that also influence my scheduling? And I want to argue to you that my ability to schedule, my ability as someone that designs schedulers and algorithms depends on two variables, transparency and control. And so I want to talk about each of these, starting with transparency. So let me give you an example that folks are probably familiar with. Let's say we're going to the train station. Now imagine the extremes of transparency as you are scheduling yourself to be at the platform on time. In one extreme, you have complete transparency. You know that that train is coming at 10:18. You schedule when you wake up and you brush your teeth and you get in your car, your taxi, and you're waiting on that platform to meet the train. And ideally, you're minimizing the time that you have to stand there and wait. Now, the other extreme is that you have no idea. All you know is that this train will depart eventually. And maybe you're waiting for Godot. You have to basically show up to the platform and hope that it will arrive. And so without control, the kind of lesson here is that you need some level of transparency. You need that train schedule. You are not controlling the train. You do not get to say, okay, conductor, I'm waking up at 6 a.m. tomorrow. I need the train at this time. But you have the train schedule, and so you have transparency. Now let's talk about control. Now, I think a really good exemplar for control is logging into a cloud and, for example, requesting a virtual machine. Now, assuming that there's not resource contention, you can typically click create, and then your VM comes up. Now, you do not care what is going on in the back end of the cloud for how they're orchestrating their VMs and how they're getting it to you. All you care is that you had complete control to click a button and then get the resource that you expected and then pay for what you expected. But in most scenarios, such as the one we're going to talk about today, it's not the extremes, right? It's going to be an intermediate level of control and transparency. And so let me give you examples of that in the real world. Sending a letter. So you can control when you put it in the box. You can control the service that you use. You control the level of service or the timing. But once you put it in that box, you are trusting the postal system or whatever service you're using that it will get your letter to where it needs to go in some amount of time. 2 to 3 days, couple of weeks. You hope that it does not get lost. Now, maybe a better example is when you order groceries that have a delivery app. So you might look at your app. Let's say you're sitting there in your pajamas and you're like, okay, my order is still 8 stops away. I do not need to schedule myself yet to change out of my pajamas and be presentable. You look at your app again and you say, I'm the next stop. I have the information I need to know that I need to get dressed. Now, in a real queue situation, what might actually happen is that you'll be spot 8, jump down to 2, and then back to 6 because other people might have priority. But this is sort of a high-level example. And so now if we visualize scheduling the grocery delivery, what we see is that we make the order. We have a period when we are waiting, we're in our pajamas, the driver is delivering to other customers, and there is some arrival time at which point we need to be presentable and the driver is going to say, hello, I'm here. I hope you are ready too. And the lesson from this is that when we don't have complete control or transparency, guaranteed and predictable is a good start. So now I want to introduce the 2Q problem, which is something that we encountered when we started to look at these separate vendor queues. So here's the basic idea. These are a bunch of vendors on bracket or bracket, which is Dirac notation, which I learned from Dan, which is really cool. So when I first saw these other vendors, I was like, not my queue, not my problem. But then in reality, someone's going to say, well, hey, can we synchronize the scheduling of these things so we don't have nodes idling and waiting? And it's like, oh, I guess I do need to think about this. So now we're going to look at that same pajama problem. That's the official name. I'm just kidding. But we're going to look at this in the context of actually quantum resources. So imagine that you just do the simplest thing you can. You submit your HPC job. It is requesting quantum from a vendor queue. It is also requesting classical resources. Your classical resources are allocated. The task gets sent off to the quantum vendor. And then what happens? You wait. You're on the train platform and you're waiting to move up in the vendor queue to run your quantum. Your classical resources, your really expensive GPUs, they're also sitting and waiting over time. Now, at some point, the quantum is going to be ready. It's going to run. You're going to get some data back, and then you can actually do compute. But those nodes were just idling and doing nothing. Ideally, you would want co-scheduling. So a scheduler that is able to say, okay, I am not going to actually have these nodes run until the quantum is ready and I know that I'm not going to be wasting them. And for example, when you have something that's running in a loop, this is immensely important because you're not just going to be firing off one task, you're going to have multiple tasks that are going back and forth between classical and quantum. Okay, so now that we're sort of moving down levels of abstraction where we started at the top, and now we're moving into quantum workload manager design, different strategies to handle the 2Q problem. When we were thinking about this, we noticed that there was kind of 2 levels of integration, and both of these are very important, but they are definitely distinct. So scheduling integration means that my scheduler understands quantum or some custom resource as a fully fledged first-class citizen resource. It is going to account for it temporally, perhaps in a resource graph or somewhere. Execution integration is predominantly wrappers, helpers that handle environment, execution, and kind of the interaction with specific quantum APIs. And so you can do one or the other, but really for a production solution, we want to have both because the scheduling is going to make sure that you don't waste resources, but the execution is going to make the experience really good for the user so they don't have to think about Okay, I'm going to manually call this and write this in my environment. So the goals that we have when we're thinking about scheduling and execution, we need co-scheduling designs that eliminate the need for these classical resources to wait. This is the 2Q problem. We need to securely handle credentials to not give users cross-exposure of application state or outputs between users. So if you share a single credential for all users on your cluster, if that's in the application environment, that means user A could technically query an API to look at results, queue status, anything for user B. We need to clearly define that separation between these two things, as I mentioned. And we need flexibility for deployment at different institution setups. And that's really kind of the spirit of a lot of these open standards projects. Okay, so if we now take those categories and we put them into buckets, this is sort of obvious. You can have a solution that just handles co-scheduling. You can have a solution that just handles execution. And what we're going to talk about today are sort of preliminary solutions that start to think about how to handle scheduling, co-scheduling, and execution. So both of them. So let's go into these designs, but I need to tell you a little bit first about Flux Framework because I'm guessing there's at least a couple of people in the room that are like, Flux, like what are you talking about? I've never heard of Flux. So Flux is the workload manager developed at Lawrence Livermore National Laboratory. It combines hierarchical job management with graph-based scheduling. We have a lot of talented developers. We've recently joined the High Performance Software Foundation, and Flux has been around almost 15 years. It hasn't been well known because we've recently just kind of put it out there. It is the system scheduler installed on the previously number one supercomputer on the top 500 for 2 years in a row. Now number 2, still really good, I think. So Fluxion is our scheduler component. And so what you're looking at here is a visual representation of a graph. This is how we model resources in Flux. So you have a cluster at the top. The cluster has children, racks. The racks have nodes, the nodes have sockets, etc. Now this is shown as a graph picture, but in the actual Fluxion scheduler, this is JSON. It's a JSON object that has nodes, it has edges. Now the really cool thing about this is that Flux does not care what these nodes and edges are. You can model your cluster, you can model your network, you can model quantum devices, you can model an ice cream shop. It is flexible to resources that exist today and into the future. This is what makes Flux really great for converged computing. This is an initiative that we've been working on for many years that combines the best of both worlds between traditional HPC and cloud. Flux itself, why is it called a framework? It's called a framework because it's modular. So if you go on GitHub, these are the projects that you will find, Flux Core, Flux Sched, and you can kind of move them in and out of different other spaces, such as Kubernetes, to come up with really interesting research projects. So Flux Sched, for example, is what we worked with early on to kind of understand this particular space. Here's a visualization of converged computing where it's in the middle of those two spaces. And what I wanted to point out here is that we're moving into kind of a new space this year where we're like, it's not just features from like cloud native and HPC, it's bringing in new custom resource types where quantum is an example. And so we're going to explore that specifically with integrations of the Flux scheduler to start. Okay, so let's jump into those designs. Now, the first environment that we decided to develop in was Kubernetes, primarily because it was easy to develop in. So we have a custom scheduler plugin called Fluence. I want to remind you that when we don't have complete controller transparency, guaranteed and predictable is a good start, and that's the approach that we'll do. Now, I want to quickly mention that Fluence is not a new project this year. It was first published in 2022 at Canopy SC as a custom scheduler plugin. And you can see in the picture that it provided a pod that was essentially running Flux to schedule your pods in Kubernetes. And it solved a lot of problems that had not been addressed at the particular time. And so just to give you a quick example, what Fluence does well, even back in the day, back in the day, like 5 years ago, right? Is it schedules gangs or groups of pods. And so what you're looking at in this plot is in blue, we have the default scheduler, no sort of knowledge about scheduling gangs together, and then orange is Fluence. And you see that the application runtime really shoots up because essentially you have gangs that are scheduled without all their friends. Okay, so they're waiting for them to be scheduled. So what we wanted to do is take Fluence and update it to actually support any kind of custom resource, including quantum. So the first thing we thought about is how do we model this in our resource graph? And this is what we decided on. We decided that a quantum device should be modeled at the same level as a rack. So when you're making a request for work to Flux, you are asking for some amount of classical compute and some amount of quantum at the same time. And then when we map Fluence or Kubernetes into this particular space, the strategy that we use is sort of, if you look at the bottom, what Fluence does is it launches a leader pod that is going to basically submit the task for your quantum work. That leader pod automatically has a sidecar that is going to monitor the queue. So a lot of these vendor APIs, they give you that little bit of transparency that allow you to see, okay, my job is number 4, number 2. My job is number 1. The quantum is ready. And so when the sidecar sees that the quantum resources are ready, it ungates the classical workers. And then we have confidence that they start running at around the same time. This is what it looks like for the user. So this is again back to like you need to make sure it's easy for the user. You add the scheduler name Fluence, you add your resources, and then there's, for example, the output that you might see. Here is some of our experiments that we've run across 3 different sizes of workers. The default scheduler, without any awareness, is in purple. Fluence is in green. And you'll notice a couple of things. One, that there's huge variability in default. So when you're waiting for these quantum queues, I had a couple wait times that were in the order of hours, meaning that my classical workers were just sitting there waiting for hours. You'll also see that there's a lot of outliers, especially for the default. Now, Fluence across the board, much lower time because we basically eliminated all of that waiting time. And another thing that Fluence does is we have a Kubernetes kubectl plugin that can basically use the user's local credentials before it even gets submit to look at some requests for what to prioritize. So for example, the user might want to minimize cost or select a queue that at the time has the minimum waiting time. Here are experiments where we demonstrated this. These were kind of simple, but they made sense. So this cost and queue selection. On the left, we can see that when you use Fluence and you ask to minimize costs, you get a very tiny cost. And then when you ask to minimize the queue depth, you get a much faster time to the result, which is a very logical result to get. Okay, so that is Kubernetes. That was our first work. And we said, okay, we like this. The next stage of work is we want to be able to take an analogous design and move it into Flux framework, move it into Flux core. And so the implementation that we have that we're about to test is going to be based on the idea of Flux with a reservation, but it's not quite a reservation. We're calling it a hold. And let me explain to you what that means. So in the first step, you start with your classical graph, and then you're going to have a subgraph where it's going to define the quantum resources. Now, in the integration, and this is a really important note, it is agnostic to the fact that you are adding a subgraph of quantum resources. All of these requests are being done to Flux with RPC calls. So for example, in the number 2, you see the call for add subgraph. That can be done by an administrator to add it to a system level instance, or it can be done by a user in their own level instance to add something else to schedule to on the fly. So the Flux integration does not care that this is quantum, but the result for this addition is that you get that graph that, for example, has your quantum devices. Once you have that graph, this is just to show that the way that we're modeling it is we're putting the vendor and the particular queue or the particular device as the type. And that's really just a query optimization at this point. A couple of design details that are not important is that we request the QPU as exclusive, and we load with a particular match format to get back all of the rich metadata that we need. Now, here's the strategy that we're going to use. We are going to basically create a reservation for the classical, but unlike a typical reservation that will be like, oh, I can run now because everything's available, this reservation is going to be held until it receives a signal that it should be unheld or released. Actually, I'll show you this in the next slide. And we have the same goals as before. We know that we're using an external queue that we don't have control over. We have very little transparency to. We don't want to have resources running that are idle. And we want for the user it to be a really simple interaction. And so the way we're going to handle that, Flux has a client plugin interface. And this is an example of the client plugin that we've written that will modify Flux Submit to allow you to put flags to request the kind of quantum that you want. So this is hugely subject to change, but this is an example where I'm asking for IBM Brisbane. What the client plugin is going to do is that it's going to basically put a hold on the classical resources, and then it's going to dispatch the scout. Just in case you're interested in, this is what a piece of the job specs for each will look like, the plugin generates. I can give you a better verbal description of what this is like. If you imagine that your entire Flux instance is a graph, when you define a job request, it's like defining a shape in the graph that you're asking for at a particular count. So when you say, I want this particular shape, we are going to do a traversal of the graph. And if we can find the correct count of that shape, that's a match. That's something that we can schedule. And so again, to map it to this picture, we are going to have a scout job that is serving as the leader. That is going to be monitoring the quantum queue. The classical resources are held. Now here's kind of the difference with Flux, and I started to allude to this. When the quantum is ready, we are going to fire an RPC, again from that scout job, that sets hold to false and releases the reservation. This RPC can only be called by the owner of the job. Everything else would be rejected because not your job. And then, of course, we run the compute, and we just need to share the session ID from the scout to the compute. There's several ways to do that. The simple way is like write it to a shared file system directory. The better way is to use the KVS, key value store. So here's an example of flags that I've made for different testing cases, mocking, so for testing on GitHub, QRMI, and then bracket. Again, these are underdeveloped, going to change, knock, knock. Okay, and the other point I want to make is just the separation, the onus of responsibility. FluxGed does not care about quantum in particular. It implements this design for hold and release, then adding a subgraph of some custom resource, being able to hold a reservation, and it has no knowledge about vendors or anything specific. The library we bring in that's going to make the call to add the subgraph, that adds the client plugin with quantum knowledge, this is a different library we have called Flux Quantum. Okay, so I want to briefly talk about workflow tools because there's been a lot of interesting discussion about how do workflow tools fit into this space. And so the question here is, can we place responsibility for coordination and execution on a workflow tool? First, I want to show you an example. So SnakeMake is a workflow tool that is very commonly used in biosciences, lesser so by physics and astrophysics and geology, I think. What you do in SnakeMake is you write a snake file, which is akin to a make file. And in the snake file, so okay, you have your rule all, that's going to be the final output. And then each rule defines inputs, outputs, and then it's a scoped piece of work that basically runs a pipeline until you get the final result. So what you can do in each of these rules is you can package expertise, application and vendor specific logic for execution. So for example, in this first rule, we have an example of what it might be provided by a vendor to initialize the session. In the second one, that would be actually running an application. And then the SnakeMake describes these things as wrappers. And so instead of me being a user and having to write a bunch of Python code and then everyone else writing a bunch of Python code and then a grad student writing Python code and having it have not best practices. There's one sort of best practice source of truth for how to create a session, for example. And so you can basically assemble these like Legos to make your different workflows. And I've actually done this in a small example, quantum wrappers right there. So here's the issue. So a workflow can orchestrate quantum, but it cannot co-schedule. So let's take a look at that exact workflow mapped out into the steps. So we might be able to serially run this, step A, then step B, then step C, we're done. That will handle the kind of the niceties of the environment, wrappers, parameters. You can customize the parameters per step. It's going to generate a DAG, directed acyclic graph. But when it comes down to it, the back end of workflow managers are executors that still submit to something that is like a workload manager. So you are still submitting to that workload manager and then monitoring and waiting. So it's great for orchestration. However, orchestration is not the same thing as co-scheduling. So for example, if we had this workflow and we tried to apply our Scout model to it, the Scout would come back and say, I'm ready. And the workflow tool would be like, great, I'm going to launch now the classical resources. But then what happens if you're waiting for the classical resources? So there's still that issue of coordination that is needed. But here's the great story. Workflow managers and workload managers, those are very similar words. I know that's Yoon's favorite thing. These work together as a team. Basically, what you want to happen is that the workflow tool is responsible for generating the DAG, providing these niceties and these wrappers, ensuring that we have validation of the environment. It's going to submit to the workload manager and trust that the workload manager is going to do the right thing with co-scheduling so that classical and quantum run at the same time, if that's what's needed. So this is sort of the future that we want. So then it goes back to the workflow manager, aggregate report, et cetera, et cetera. Okay, so let's quickly summarize. What I didn't talk about, I want to include this QR code in case you're interested. This is the early work that we did up to the last two projects that I talked about today. Now here is what we actually did cover. We talked about how application design should be the primary driver of scheduler design. This is not an if you build it, they will come. If you build it, then they will not notice because it does not fit their use cases. The second Q problem, extended to the NQ problem when the future gets more complicated than it already is, requires intelligent coordination of different queues. We can model quantum devices as first-class citizens in a resource graph. This is a sort of fluxism. And workflow tools are valuable to collaborate to optimally package steps, execute, and kind of delegate to the workload manager to co-schedule. So some feedback for vendors and some of our future work. This feedback is actually really important for us because I want to tell you what I would like. So for QRMI, there's an acquire function that essentially sends a no-op session ID back. It's not really a promise of anything. It's just sort of a session ID. I think what would be really cool is that if that session ID was able to get it back, but instead of being required to actually submit your task, so again, the running of the application is paired with that acquire, it just serves as a request that gets a foot in the queue, decoupled from the application. That will better allow our schedulers to be able to get their foot in the queue and be totally separate from the needs of the application. And then when that happens, there's kind of two things we can do. We can poll for the ID, which is what we do today. Works today, that's great. But in the future, it would be really great to get event-driven notifications so we don't have to poll. So future work for us, we have the first implementation in FluxCore done. So we're going to do more experiments. Oops. No. So we're going to do more experiments. We're going to discuss other designs. So for example, Flux supports kinds of grow and shrink of both the resource graph for the scheduler and the job, not in production yet, but just in FluxGed. So you can imagine that we actually just have one job that starts small, monitors, waits for the resources. When the quantum is ready, then the job grows. So that's another design we can consider. And then we also are going to be doing work to extend this external queue to work with devices locally for which we have both transparency and control. So my prediction is that it's going to be easier, but I shouldn't say that. Knock on wood, knock on wood. So, and here's the really great thing. Quantum awareness can be extended to other schedulers with analogous design. So on that note, thank you for having us. I will stop sharing my screen and let's open it up for questions and discussion.
Okay, thanks, Vanessa.
I have.
Okay, go ahead, Doug.
And it's too bad Doug's not here because I would like to get both Vanessa and Doug's thoughts on this. But I've heard about, two resource management interfaces and their future plans. And now I'm seeing two schedulers and I'm starting to see some overlap and I'm getting a bit worried here. Things like talking to Amazon's cloud, like federating, scheduling. It almost feels like the resource management interfaces are trying to participate in the workflow management, yet we have workflow managers. So, Vanessa, do you see that too, or do you see this working at, given future plans of the resource management interfaces to do a lot of this work?
So let me try to understand what you're asking. You're noticing that projects like QDMI, QRMI, are trying to do most of the control, but then also the workload manager developers are doing the same thing? I'm not sure I'm understanding your question.
Yeah, I mean, maybe I'm seeing it wrong, but I sort of was recognizing a potential overlap of responsibility.
So I have not used QDMI yet, so I have only the talk. I was actually sitting in the front row of one of Martin's talks, so I have that understanding. The way I think about it is that those libraries are providing like the API calls that will empower a workload manager developer, so us working on Flux, to be able to get the information that we need and make requests for what we need. So we are not, if we need an interface to interact with Rigetti, for example, we have no transparency into Rigetti, but Rigetti can give us this standard interface that we can implement somewhere in FluxGet and FluxCore to help orchestrate the jobs, the classical and the quantum resources. So my impression is that this is not like stepping on toes, that these different projects are very much going to be needed to work together.
You're really interested in the workflow aspect and the intersection with workload managers?
Yeah, well, yeah, I just want to see that it's clear that if I'm using Slurm or I'm using Flux, it's dealing with like multiple QPUs, both on-premise and remote, and figuring out the scheduling aspect of it. Yet the resource management interfaces are simply giving me that window of everything with that one particular QPU here, and then the window to that other QPU there, whether it's remote, and not let them do anything that would interfere with the scheduler's ability to do the job as well. And I noticed that in QRMI, you were talking about talking to the Amazon bracket system yourself underneath QRMI's interface, as opposed to above it, which is what I would imagine Flux might want to do.
Oh, sorry. So I wasn't using these experiments with bracket. We're not using QRMI. The experiments with bracket that we're deploying a sidecar, we're just interacting directly with bracket.
Right. So
QRMI would be a different sidecar that has interfaces, the libraries that QRMI provides.
So QDMI has integrated with bracket.
Okay.
Okay. And I don't really see a disconnect there. QRMI could also provide the front end for Amazon bracket. Now, would you want to go directly bracket? That's a different question. That's definitely, would you want to try to take advantage of some of that platform?
Again, that's the question. Is that a responsibility? Is that a workflow manager responsibility or resource manager responsibility? I'm just trying to split it up. I guess what I'm worried about is bloatware. I mean, if the resource managers are starting to do everything,
Yeah.
it makes it.
No, they're definitely not. So
I mean, from our perspective, right, I want workload manager at the lowest level to get the allocation of the resources and manage that. Now, I have my company builds products that are both, we build the workflow manager too, but that's how I'm dividing it.
Okay.
And I'll try to talk a little bit about that.
I think we're trying. I think QDMI and QRMI are just trying to make the resource available to the workload. Beyond that, I don't think we want to do anything like schedule or anything like that.
But I strongly agree that there is a tendency to push things all into the scheduler, which has cause. And
Yeah, I agree.
don't want to do that either.
Okay, okay.
Okay, good. Okay, any other questions?
Um,
Yeah.